Hello and welcome to this edition, the 11/17/2017, 11/18/2017 version of the SkyTour LiveStream. Now, tonight we are going to look at amazing deep sky wonders because we've got plenty to look at. However, we're also going to do a kind of a weird night. We're going to split things up a little bit and come back a little bit later to take a look at some of the wonderful features in Orion. Now, it's also the Leonids night, and I haven't lost sight of that. And if I can remain warm enough, I will show us some Leonids later on. That'll be late. Anyway, we'll see you soon. Good evening, everybody, and welcome to the SkyTour LiveStream. I want to welcome Amanda, as always. Hi, Amanda. How are you?
Hi, Mark. Hey, Al. How's it going, everybody?
It is probably going to go very well tonight, hopefully. I mean, it's very cold, which means the air is very dry, very still. Actually, right now tonight didn't have to be dry, but it is. And it is also going to be a nice night to look at the Leonids, and I know Bill New York Skywatcher, our good friend and buddy, is off doing that right now. And they'll be more prominent between midnight and 6 in the morning, but that's because of the fact that the meteors will be chasing the Earth after that, because the Earth will have rotated past the midpoint of its orbit where it won't be now. You know, the meteors.
Can you explain that in more detail? Because I think that's really interesting.
Yeah, I mean, when you see the meteors earlier in the evening, they appear to go faster.
Well, relative to the peak.
Relative to the peak,
like,
right?
Can you explain like what a meteor shower is? Like, what is the Leonids? What are people looking at tonight?
Oh, okay. Well,
thank you.
When we look at, I make these assumptions sometimes that people may know these things.
Well, just in case if someone's tuning in and they don't know, I mean,
yeah,
we all have to start somewhere. So
that's absolutely true, as I did, you know, myself. Exactly. So yeah, so when we look at a meteor shower, what is a meteor shower? Well, they're basically little grains of sand. No lie, they're only about the size of the grains of sand. They're pieces of elemental dust that was left over as a comet passed by. Now, what's it mean when a comet passes by? It means that a comet, like a planet, is in orbit around our star. However, the comets that are periodic, those that come back, are in an established orbit. Those that are not periodic are comets that will come by just one time, and then they're gone for good. All right? It's one-time appearance. Sometimes comets that are periodic and orbit the sun on a routine basis, like Halley's Comet, comets like that will, over time, evaporate because successive passes by our sun will disperse, evaporate, and remove content from the comet, and so it'll get smaller and smaller and smaller until it breaks apart, as Comet Shoemaker-Levy broke apart as it approached Jupiter. Enough of the comet had been ablated or melted away over a long period of time that it was able to be broken apart by the gravity of Jupiter, and it ended up being a string of impacts on Jupiter's upper atmosphere, which I could even see with my telescope. I actually saw them as they were happening. It was just amazing to see these black spots on the upper cloud decks of Jupiter. You know, so as a comet passes by, It's made of dust, it's made of ices, and it's made of other hydrocarbon compounds and other compounds that are on its surface. And a comet doesn't have very big gravity, it doesn't have a high gravitational pull. So what can happen is, as dust is expelled off the comet from solar energy impacting it and causing the areas within the comet to get excitable and do what's called outgassing. So little bursts of gas that are trapped inside the cometary components will come bursting out. And this outgassing causes a cloud to appear around the comet. That's called the coma, like in a coma. And that coma ends up becoming a sort of like a ball around the head of the comet. That makes it fuzzy. But then, as it's moving through space, the debris that's coming off the comet just sort of falls behind the comet. As the comet's being pulled toward the sun, it leaves it behind. And thus, that dust tail that you see becomes the meteor shower later. Now, there's also a tail on the comet that's created from the high energy particles from the sun that's impacting it. That's called the ion tail on the comet. And that ion tail actually is always pointing directly away from the sun, because it's a reaction, it's an energetic chemical reaction and electromagnetic process that we're seeing. So we'll find that the ion tail always points away from the sun. So you can have the odd case where you see the dust tail of the comet in the sky, and then, say, to the right of the comet, and then to the left of the comet, you see another thing sticking off. And you say, wait, a comet has two tails going in two different directions? And yes, because that just shows that the dust tail is trailing along the path of the comet from where it was. But the ion tail is simply pointing directly away from the sun at all times. So as the comet comes around the sun, the ion tail swings right around and points away from the sun at all times. So as the comet's leaving the sun, the comet can look like it's heading into its own ion tail. and it is. But it's a kind of a weird thing. So, but the dust is the important thing. The dust is what the Leonid meteor shower is all about. It's what the Persians are all about. It's what the Orionids were all about. So we see this dust, and when it enters the Earth's atmosphere, of course, it's coming at a very high rate of speed, several tens of thousands of miles an hour perhaps, or let's say 20,000 miles an hour. And it can end up impacting the upper atmosphere as it does, and when it does that, there's not a lot of what's the word I want to use here? Not a lot of forgiveness in our upper atmosphere for particles entering the atmosphere at a high speed. Friction starts to affect these particles almost immediately, and as soon as there's enough friction, then the cometary debris and these meteors will end up burning, and thus they are gone within a split second many times. As you looked in the night sky, sometimes you don't even have enough time to say to someone next to you, hey, look at that meteor. Okay? Because when the burning begins, it's only the size of a grain of sand. Once that burning begins, it's a catastrophic process that happens very quickly. However, sometimes you get objects that are a little bigger than this grain of sand, maybe the size of a marble, and it takes them a little longer to burn up. And if they are moving slower into the atmosphere, they'll also take a longer time to burn up. And you get a chance to see them. Sometimes meteors will strike the Earth at a very direct angle, and sometimes they'll make a glancing blow where they won't actually strike much of the atmosphere before they skip back off into space. We call those Earth grazers, like, grazing cattle, but Earth grazers. They just barely nick the upper atmosphere and then they keep going. Usually when you see those, they look like they go horizon to horizon, and they leave a smoke trail. We call that a meteor train behind them. And that smoke trail is something that's very interesting, because if you look at that smoke trail, it can kind of give you hints as to how big the original object might have been, and the speed and so forth. A couple years ago over Russia, a fairly good-sized meteor came into the atmosphere, And it only ever reached the upper stratosphere. However, the shock wave from the impact, when it actually came down a little lower into the atmosphere, the meteor is coming in at a high rate of speed, and so when it starts to hit more atmosphere, it hits more atmosphere in a split second. And when it does that, it's like hitting a wall. All right, you've always heard the adage, well, if you jump off a tall cliff into the water, it's like hitting concrete. Well, that's true. Yet you can jump right off the shore into the water with no problem. You don't feel a slap. It doesn't knock you out. Well, in this case of a meteor, think of the water as the atmosphere, right? If a meteor is coming in, it feels very little atmosphere at first, but then it very rapidly gets to a point where the atmosphere is thick enough to begin burning the meteor, and then very, very quickly after that, because of the speed at which it's moving, the meteor will then hit the wall. And when it does that, if it's big enough, it could explode. And when it explodes, because it's happening within a medium, that is the air, it can generate a big shock wave. And this shock wave is something that we saw with the Russian impact. That Russian meteor blew out windows, injured people. People got, pummeled with glass from doors that were blown out. I watched the metal security door bend from the shock wave and go shooting in to the room. Unbelievable. I mean, really powerful. So, and that meteor probably was just a few feet across. It doesn't have to be very large, because what happens is you're converting all this, what we call kinetic energy, the energy of motion, into heat. And when the meteor can't withstand that anymore, it explodes because it overwhelms the structure, and the structure of the meteor can no longer handle that. And that explosion generates a massive shock wave that's, the same kind of magnitude you might expect from something that's like something hitting a wall. And that's pretty hefty and pretty large. So that all said, I think it's interesting to talk about, but we also have to keep in mind that we're not going to be, seeing meteors right away today. I want to show you a few other things first, and then we'll do that. I also want to take us to Orion when it comes up, and we're going to look at the Pleiades, and we're going to look at a few really cool stars, and so forth. Now, to finish answering Amanda's question from before, okay, the meteor showers that we are going to see from the Leonids are the remains of a cometary dust tail. And as I said, it's hard to believe that what you see in the sky is something that's only the size of a grain of sand in general, but it's true. That shows you how much energy that gets expended, all right, when this thing is burnt up. You're watching physics in action here, okay? So it's a very, very instructional, educational thing to see. I saw a Leonid a couple years ago. I was just looking out my living room window, and I watched this Leonid meteor come in, and it was after midnight, and it left a smoke trail behind it, a meteor train, as we said, and it actually broke up, and I saw it break up into distinct pieces, and then the meteor train began to glow green, and it was fantastic. It was just beautiful, and so the green color, of course, is because of interactions with molecules in our atmosphere, and it's pretty cool when you see it happen, and then that stays there in the sky for, I don't know, about 6 to 8 minutes, and it started to fade away over time. But boy, that was just really pretty to see that. Neat stuff. And so the meteor shower tonight, don't miss it. Check out Building Arc Skywatcher as well. And like I said, if I have battery that will last, we're going to actually, I may set the camera up on the tripod later on and check it out. I won't be staying up all night. That's Bill. He's crazy. But then again, Bill is also, doing a night shift for KGRA, so he has to be up. So why not stream, right? Why not stream the Leonid meteor shower? But tonight, I wanted to take us to a few things. Since there's no moon, I'd like to take us to check out a few things that are kind of cool. one such place that I want to check out with you right away is this guy coming up. All right, this is a, you saw it in the picture just briefly a moment ago. This is a galaxy that is often left out when people go searching for the Andromeda Galaxy. They see it, and when they see the Andromeda Galaxy, they're, hang on, let me let it do this. Okay, sorry, I realized that I was competing with the sound there of that. So, all right, let me, this is called the Pinwheel Galaxy M33, and I did put a photo up of it online and SkyTour LiveStream site, companion site, and it was a stacked photo processed pretty extensively, and it was really pretty. So I wanted to do it again, but I'm going to show it to you live because I don't believe we did it live, and there's something that is amazing to see when you look at it live. And we'll do that right now. So let me just go look at this. Now this is 30 seconds to 16,000. Okay, we're going to do a 30-second at 16,000 shot. This one, it's probably going to be in the lower right quadrant, and I'll probably have to do it again. And I forgot that that's going to happen. So this is sort of a wasted shot. I apologize. But I just wanted to make sure that everybody understands that this particular galaxy, the Pinwheel Galaxy like this is a galaxy that's 2.7 million light years away. And the Andromeda Galaxy is 2 million light years away. So they actually are pretty close in space, but they're not interacting directly with each other. And the fact that these two galaxies are here, like this, Andromeda and M33, you'd be thinking, wow, they must be interacting or whatever. They're close to each other in space. Well, the fact is, okay, the Andromeda Galaxy is heading toward our galaxy, all right, and they're, the galaxies, the Andromeda Galaxy and our own, is going to collide with ours at a future point. Actually, the word collide is the wrong word. You really want to say merge with ours, and that's what it's going to do. And it's in the lower right quadrant, so I'm going to have to bring it up. Hold on a sec. Okay, I'm going to raise this up. Just a minute.
And I just put the link for the SkyTour LiveStream group on Facebook. And just a reminder, all the pictures that he's taking tonight, he will put on that Facebook group. And soon we'll have a site for people that don't like Facebook for some reason and aren't on Facebook. So those that are, please check it out and check out all the awesome pictures. And those that aren't, please be patient. And we'll do what we can. Or subscribe and hit the bell here on YouTube, and you can see it all live.
That's right.
Or you can watch it back. He keeps all these episodes too. So.
Yeah, that's true. Okay, I see it there. I just had to get it. I can differentiate the certain types of fuzz from other types of fuzz on the screen, and certain types of fuzz are the fuzz of the object I'm looking for, and others are not. So now it's going to be in the view. So this is going to be, and just to confirm that, I'm going to do a shot for only 6 seconds at 160,000 ISO sensitivity, and now you'll see the galaxy should be right about in the center. It might be off a little bit. And there it is, right? Just to the right of center a little bit. You saw that there, I hope.
I saw a lot of pretty color.
Yeah.
Yes.
Yeah, and the galaxy's there. So this is my finder shot. This is the one that tells me what we're doing. I'm not using a practical sensitivity right now. We got to use something that's a little bit more practical for this. So I'm going to drop us down to 16,000 ISO and put us up to 30 seconds. All right, and now when we take a picture, all right, it's going to go for a while, a little bit. Now there's something interesting in this galaxy that I want to show you, because you're familiar with the Orion Nebula in our galaxy, okay? It's in the Orion arm of our galaxy, and in the Orion Nebula is a stellar nursery. It's a place where stars are being born, and if we get a chance, hopefully we'll get to see the Orion Nebula later on as it arises. But what's interesting about all this is that stellar nursery we see, and it's in our galaxy. So you think, wow, they must exist in other galaxies, right? Don't these stellar nurseries, these are the regions I've called before H2 regions, that is H Roman numeral 2 regions. And these H2 regions are singly ionized hydrogen, all right? And what happens is when hydrogen is hit by ultraviolet radiation, the hydrogen molecule, the electron, can be thrown right off the atom, basically. And when it is, it's beautiful. When it is, then what happens is you might see. I'm just going to get this back for a sec so you can see it. My thumb was cold. Okay, let's see. Here we go. So when you look at it, when you look at a hydrogen 2 region, H2, when the hydrogen atom is excited in an H2 region by a hot, bright young star nearby, the electron, it's a proton and an electron on a hydrogen atom. And in what's called the ground state, where there's no positive or negative charge, okay, a proton is positive and an electron is negative, so the plus and the minus cancel out to zero charge, with the electron, being the negative charge. And when the electron is thrown off the atom because it absorbs all this energy, it goes to a very high state of energy, okay? And when it does that, sometimes it leaves the atom for a period of time, and it'll recombine later, and that later may only be a few milliseconds later, all right? But when it recombines and comes back into the atom, it finds it's losing energy. As it finds a energy state that it can enter that's reasonable, what happens is that atom, that electron, comes back in, and as it loses energy, when it loses energy, what happens is it emits light. And that light is a very characteristic reddish color for that particular hydrogen band. And this hydrogen band is something that we look for out in space, and we see a lot of red nebulae, and the Orion Nebula has a lot of red coloration in it, as you may know. If you don't know, then hopefully we'll see that a little bit later anyway. And so when we look at a galaxy like this one right here, we're looking at M33, Messier 33, in the constellation of Triangulum. And let's zoom in a bit. And now if we zoom in, okay, you can see the core of the galaxy. It's got those dark lanes, those dark knotty clouds of dust in there. And if you notice, right to the right and up, right there in the center of the screen almost, you see that pinkish region? You're actually looking at an H2 region that is a stellar nursery in the Triangulum Galaxy, 2.7 or 2.8 million light years away. Isn't that crazy? There's one right there. Now, there's also a number of them. This galaxy is filled with them, okay? And if we move around, you can see some green lines here from the process I had to use. If you look right there on the right side, okay, that one, okay, right, let me zoom in from as far as I go. There's one there. It's just to the right of center. It's just, I can't move over anymore. That's another one, okay? And that's actually, what that is actually, that is likely a supernova remnant. It actually has a ring. It's a ring around an area in the galaxy. So it's very, very cool. And now, if we move over to the left a little bit, let's see if I can get over to the left a little bit. We'll see that we have this bright one up top here. You see that? Okay, we got that bright one right there. That is a very, very well-known stellar nursery. And it's actually reddish as well, but because it's much brighter than the others and a little even brighter than the galaxy itself, it looks kind of like a bluish white here. Now I am using a special filter to keep, give us the best data we can get. And we're watching this thing, from, like I said, 2.8 million years ago. That's when the light left it. And so, but this is a stellar nursery that's in that galaxy, far, far away. Ooh, like Star Wars, So, I'm really, sorry, I'm really impressed with the ability of the telescope to show us these things. And then there's the spiral arms. You can barely see them here, because the area here is not perfectly dark, but it's dark enough that we can see spiral arms and some nice features. There's another H2 region right there in the center of the screen now. Okay, that one, there's probably about, I don't know, I'd say probably 50 or 60 H2 regions that are in this galaxy. And this galaxy is not terribly dim, but not terribly bright. Now, oddly, if we look at the Andromeda Galaxy, which we'll do next, we don't see these as prevalent. But it doesn't mean they're not there, because they are. It's just that with the overall glow that we see, we can't actually see them. Let me just do this here. I'm just trying to figure out if my camera's doing some wacky things again. No, okay. So anyway, you can actually see, and those green lines are that's just, again, those are artifacts. I'd get rid of those in processing, not to worry. You see vertical green lines. So even in a galaxy far away, we can see where stars are being formed. And that's exactly what we're seeing here, okay? So, and this is the view. There's only one star visible in that view, okay? It's in the upper left. And everything else is pretty much, lost. And now this galaxy is almost overhead, so it's actually in pretty good location. But now let's take a look, and let's just zip over to its neighbor. All right, and the neighbor, of course, is the Andromeda Galaxy, our favorite, everybody's favorite. And what we'll do is we'll make sure that we'll do our acquisition frame, make sure we have it, because it's definitely going to be nearby. Okay, so I see it there, and you can already see it in the lower right.
I do.
Yeah,
it's very pretty.
Yeah, and that's just a glow. I mean, you can actually see it. So let me just I will now just pull this up a little. Actually, keep my acquisition going a little longer, and then just bring it up. The other thing is, you don't always want to. You don't always want to like center on the galaxy, for instance, because that may not be where all the action is. You might be wanting to see something down below, okay, like down here, okay, and you say, well, wait, the center of the galaxy is to the upper left now, and yes, it is, but the galaxy is rather extensive, especially the Andromeda Galaxy. So let's do a photo. Let's see, we're gonna do. We'll do 30 seconds at 20,000, okay? And let's see what let's see what we get. I'm wearing big giant mittens, so it's problematic. All right, 30 seconds at 20,000 ISO sensitivity. And now Andromeda is, like I said, it's Andromeda has close to 1 trillion stars, as opposed to our highest number, which might be about 400 billion. And the Andromeda Galaxy is actually being 2 million light years away. It's close by galactic standards. So in the sky, it takes up several degrees of sky. So it's not small. I mean, 3 degrees minimally, in the sky. So it's actually a really extensive galaxy. And it also has 2 companion galaxies, which I know that people are aware of these companion galaxies. But what they're not aware generally, because we're not in the southern hemisphere, is that we too have companion galaxies that surround us. And our companion galaxies, that's beautiful.
Wow.
Our companion galaxies are called the Magellanic Clouds, because they were visible from the southern hemisphere, and so as such, they're really a fixture that we just don't get to see. But they're visible to the eye. You can look up in the sky and see these fuzzy patches in the sky from the southern hemisphere. It's amazing, you know, and we just don't get to see that here. But we have the Andromeda Galaxy, and they don't, you know. So we can show the Andromeda Galaxy. Now, the folks down in the southern hemisphere, though, they did get to see something really amazing one time. In 1987, they actually saw a supernova in the Magellanic Cloud. All right, a star blew up, and it was in the what's called the Eta Carina Nebula. Eta being a Greek letter Eta, E-T-A, and Carina, the constellation within which the Magellanic Cloud is in. And they saw this. They saw this bright star suddenly appear. Well, when that star suddenly appeared, what also happened was that the stars it was exploding into a supernova, as I said, and as it did so, material started moving out away from that star. And what they saw, they actually saw what's called the light echo. They saw the speed of light. They saw light as it was impacting the debris, and not, I say impacting, as it was illuminating the cloud around it as it was expanding out. And so they actually saw this light echo. And it's actually a video you can actually go look and download, and it's really something else to see. You're actually watching, you know, the physics of light in action. You're actually seeing it right there. Now, in the same way, we also find that, and I apologize for clearing my throat. It's very cold, and you know, when it's cold, my you know, I get a little I have a problem.
You should show them how much you're bundled up, and they will appreciate how cold it is, and you sit out there for hours for us. So hit that thumbs up, people.
Oh, thanks, guys.
Give them a warm feeling since it's freezing to death.
Yeah, I mean, I will have to take a break, and you know, at some point, and then we'll come back. But there's several other things I want to show you before we do that. But first of all, notice here in the Andromeda Galaxy, we don't actually see an obvious H2 region. Okay, now they're here, all right, but we just don't see them as obviously because some galaxies have a finer resolution to their H2 regions than say the Triangulum Galaxy does. Triangulum Galaxy is pretty odd. Then there's galaxies that are basically so filled with stars being formed in these regions that the entire galaxy, or a great part of the galaxy, actually looks like one giant H2 region. One of those galaxies is actually one that used to be called the Exploding Galaxy, and now it's called the Starburst Galaxy because they realized that starburst formation these stars are forming at a rapid rate in this galaxy. And that galaxy is none other than M82, which is a galaxy in the constellation of the Great Bear, or Ursa Major. And we can't see it now. It never goes below the horizon, but it does go below the trees and into, like, you know, other obstructive areas, and we can't see it. Hang on, I got to take a Snapple break here. Yeah. Oh, it's cold. Yeah, cold liquid is sometimes better. So this is a beautiful. Looks stunning. And I've taken a number of photos of this that really look pretty. And I really like doing that. I'm glad that you guys like this stuff. I really am, because I just Love it. It's just...
Speaking of people liking stuff, Heidi is in the house.
Heidi, what's happening, girl? What's happening?
She wanted me to let you know that she absolutely loved the Ian Gunner interview, and that he was thrilled to pieces about it too. So.
Oh, that's nice. Yeah, Ian Gunner has been in Bill's chat, and he's been, I think, in P&K. I don't remember seeing him in mine. Do you?
I know the name, but I don't think I've seen him in this stream.
Okay.
But I do recognize the name somehow.
Okay. Well, Ian has his own show, and he's actually, he actually had wanted to have me on for a while, and so I went on and we did this interview, and as always, it's always the same thing. When I get on the interviews, I start doing them. The people that I'm talking to, we go on longer than we should, and it was a pre-recorded interview, so we went on from like noon till 3:40 or so, and it was supposed to be 2 40-minute segments. All right, so we had a lot to talk about, a lot going on, a lot of things to go through. So it was pretty neat to spend time with Ian, and he was very, very kind to me, very nice, and his cohort in crime there, Chris, was really cool too. But it was neat, and it was a good interview. I enjoyed it, and he wants to have me on again, so that'd be fun. Yeah, but thank you, Heidi, for that. I'm glad you enjoyed it, because I enjoyed doing it.
And I know you were on Paulino's show last Sunday, was it? Sunday afternoon, I believe. I think I posted it, and I think a few people were planning on tuning in, so that one went well, did it?
It did, except I was actually late, because I was actually, what happened was, I haven't posted any photos of this, but the SkyTour LiveStream Observatory was seriously damaged in a windstorm, and the shutters that opened to allow the telescope to look out were torn right off the building. And of course, now luckily it wasn't associated with rain. If it was, then I'd have all kinds of damage in here, but luckily I didn't. But what I did was I ended up staying up most of the night. In the middle of it was 25 degrees during the day and 15 at night, and I was out here trying to repair this dome to get this SkyTour back up and running, because I just couldn't do without the SkyTour LiveStream, So I ended up repairing it all night long almost, and then I slept for a couple hours in the morning, and then worked on it all the following day, and then again stayed up most of the following night, and then by the time it was time for Paulino's show, I had just fallen asleep after, just for 2 hours I had been asleep. And I got a phone call, and my phone was ringing, and I answered it, and it was Ben Eno. Said, "Hey, you around? You're supposed to be in the show with us." I went, "Oh, no!" And I came on and recovered it, hopefully. And Paul's a great guy, Paul Eno. He has his website is behindtheparanormal.com. And Paul and I have spent a lot of time. We've known each other for years now. And he's a good guy, and he's someone that's worth listening to and worth seeing talk. He's written a number of books on paranormal activity. And, let's be honest, okay? For those of you that don't know Paul, he was a priest. He went to seminary school. He was going to do that for his life. But then, his path took him to a different place, family and so forth, and so he didn't, stick around in that career path very long. And then he started seeing and getting these paranormal things happening. And he saw them because of people that were saying they were possessed by demons. And then it turned out that these were actually paranormal things, perhaps parallel universe intersects, which is a term I coined, where parallel universes are bleeding through into our own. Okay, now parallel universe doesn't mean from the Andromeda Galaxy to us. That's all the same universe when we're talking about the Andromeda Galaxy and the most distant thing we can see in our galaxy, or our universe. That's all the same universe. We're talking about a bleed through. Maybe we'll find out that black holes are drains into another universe. We don't know. But I do think it's interesting to talk about that stuff, And so Paul and I, we get along. We talk about the multiverse a lot. That is the concept of parallel universes. And I had an experience here, which I can only liken to a parallel universe intersection. A case where I was actually, and I'm looking up something. I want to go to another thing while we're talking here. The thing that happened to me was I was in my shop working on a movie prop for a movie we were doing up at the studio with Doug Trumbull. And as I was working on this, I realized that, I kept seeing these strange objects out of the corner of my eye at first, and then I would look at them, and they would be directly in front of me. I'd see them; they would actually be there. I'm like, well, what are those? What is this? I have no idea what these are, and what they were. They looked like a little mouse or something like that, but it was semi-transparent. And I'm like, whoa, what's going on? And I began, it was something that had started earlier. And I was looking at these things that were kind of, it was creepy to see these things because I didn't know what they were. And I just made the assumption, that they were like something wrong with my eyes, okay? But they weren't. It was something that was actually there. I'm moving, just so you know. And, let's see. Oh, that's a little low still, but we might be able to salvage this. Let's see what we can see. It's not the Orion Nebula yet. But so when I saw these objects in my vision, I was stunned, and I actually started seeing people, and I was hearing people talking that weren't there. I heard my kids, in fact, when I was in my office. I heard my kids talking upstairs. And it was like after midnight. I'm going like, why are they upstairs? They're talking so loud. They're going to wake everybody up in the house. So I ran upstairs quietly, and I went in the living room to yell at them, and there was nobody there, and it was dark. I was like, whoa. And I could still hear the voices, and they were coming from somewhere in the room, and I turned on the lights. I'm looking around going, somebody leave a radio on or something? But it sounded like it was in my head almost. And there was nothing there. So I was kind of, thrown by this, and so I didn't know what to make of it. But what I did was I ended up focusing on what to do about this this stuff that I was seeing all the time. And so what I ended up doing was I ended up being a good observer is what I did. So I actually started watching these things and figuring out, okay, this looks like a person to me. Okay, I don't know whether this is a person or what, but it looks like a person. And so I just said, okay, if this is a person, this is what it looked like. This is what I think the person was wearing, if you could think of them as wearing anything. And so I ended up logging this data, that basically just trying to figure out what they might be, what these things might be. Well, anyway, I was in my shop working on this this prop, and this was probably a good 2 years into documenting seeing things. And I'll tell you what I thought. Okay, about 27 years ago, there it is. About 27 years ago, I needed brain surgery, or I would have died. I had 8 weeks to live. I mean, just the doctor told me that outright. There was something going on in my head. They didn't know what it was, and I had to have brain surgery, or else I would die. So I said, okay, can you do it now? And he says, yeah, well, not really, but normally we schedule these things, 8 weeks or so in advance, but we don't have 8 weeks with you, so we would really like you to come in and get this done as soon as possible. So I did. I went in, I got it done. Well, anyway, when I did that, I figured that maybe everything I was seeing and all these voices I was hearing, maybe this was actually just an artifact, something associated with the healing process going on in my brain. But it was 26 years after the surgery that this was starting to show up, and that was kind of weird to me. I didn't know why that would happen then at all. Okay, I went too far. So the bottom line is that I ended up actually taking some time to understand what was going on with my brain, trying to figure out. I got MRIs, I got CAT scans. Nothing was wrong. Okay, everything fine. The brain was fine now. So that said, I was like, all right, well, don't know what to say. I guess maybe, I'm, seeing some strange things. I don't know what it is, and I figured the doctors just didn't know what this was. So let's go to now the scene where I am now in my shop working on this prop. As I'm working on this prop, I see this thing that looks for all the world like a semi-transparent dog come into the shop. No lie. And in fact, it even looked like a Pekingese type dog because it was sort of like a short, round, kind of little bouncy gait. And I'm thinking, okay, I'm seeing things. And I'm looking straight at it, by the way. I'm not to the side or doing anything like this. It wasn't out of the corner of my eye like, we can see. This was looking right at it. And when I did that, I saw it lay down on the floor in my shop, and I stared at it, and then I just said, you know what, screw this. I got up and I went over to it, and I'm staring at it, and I'm looking right down at it. I'm doing 30 seconds at 12,800 right now, by the way. And as I'm looking at it, I'm realizing that I'm seeing the other side of it. And I thought my brain was just replaying video that it had seen at some earlier point. And I figured, all right, well, if it's doing that, then maybe what I'm looking at is, a kind of a replay, Well, when you see a replay on TV, you're seeing it in 2 dimensions, and just with your eyes, it would be a replay in 2 dimensions. You wouldn't see the far side of it because the far side of it would be completely, it'd be completely invisible to your eye. And if you never saw it, you can't invent it, So, as it turns out, I'm looking at this thing. I walk over to it, and I can see that it has some form on the far side where I wasn't able to see. And I'm thinking, well, either my brain is really good at manufacturing this, or something else is going on here, because I wouldn't be able to see the far side of this dog if this is what it is. So what I did was I stepped on it. I stepped in the space that it occupied. And when I did that, everything changed. And I'll tell you why. Because at that point, what happened was the object, the thing, whatever it was, okay, it actually yanked my foot out from under me as it ran out of the room. It registered that I stepped on it, and it ran out of my shop. When it did, it yanked my foot. I mean, just imagine someone tying a bungee cord around the base of your foot and running away from you as fast as they could. You'd feel the tension increasing, and you'd be fighting it the whole way, as I was. I could feel it increasing, and then, bam! It reaches a certain point, and that leg snaps out from under you. The last thing I remember seeing is my foot up against the lights at the ceiling, and then I feel this pain and see lights from hitting my head on the floor, the concrete floor in my shop. And it was because this thing ripped my leg out from under me. I had no idea what I was looking at. I had no idea what this thing was. But as I started to put it all together, I started to think, this is what people call ghosts. This is what people think ghosts are. Maybe what ghosts are is actually this bleed through from a parallel universe that we all see in the natural world. Maybe this is just an ordinary thing that we see. And so that led me to this other conclusion that perhaps this was what I call a parallel universe intersect, an area where the 2 universes are kind of overlapping a little bit, and you can actually visit them. You can actually see them. Okay, and that's something that's crazy, as is this thing on the screen. Wow. So does anybody in the group know what this is? Yes, I've shifted to astronomy again. This object I just came to. I'll just tell you because I'm sure people would recognize it. This is the Crab Nebula in Taurus. This is the remains of a supernova remnant. I mean, it's actually a supernova remnant. Yeah, the remains of a star. That's pretty cool. I have never seen this until tonight, right now, and it's just beautiful.
You've seen the Crab Nebula before?
Yes, but it was a very lousy night, and right now it's still low to the horizon, as you can see by that bright blue background. It's still pretty bright, Man, I'm going to try something else. I might not have to go so bright. Let's try this. Let me see if I can shoot this at... instead of 12,800, I'm going to do it for 30 seconds at 10,000 ISO and see what we get. Man, even with all my warming stuff, I'm beginning to shiver a little bit. So I'm gonna have to figure something out here. I can't warm this place up. You can't do that. But
well, you look nice and bundled heading out anyway, so
I know I probably need to get another coat or something. Probably need another additional coat and another sweatshirt, another coat. My feet are reasonably okay because those little heater pads are in there just fine, and that seems to be working. My thumbs are very cold because I have my thumbs exposed a little bit. That's funny. Yeah. Oh, that's actually better. That was actually a little better when you see it that way. When you see see that? There we go. And the focus is reasonable. Yeah, so this is, with some processing, this is going to look really pretty. This will be really, really pretty.
Who is Stuart? You didn't name your... No, your dome's name's not Stuart.
No. Stuart's one of the minions. And that's I dressed the dome up as Stuart, the minion, for Halloween.
Oh my god. Is he the one with the glasses?
Yeah, well, no, Stuart is the minion that has the one eye.
Oh.
You know what I'm talking
about? Is there a tall one with glasses?
Well, they have goggles. They're like goggles that they wear. And they're funny. And they talk with a funny voice like, "Oh, banana! Hey, banana! Whoa!" That's like really funny.
Well, one of them was voiced by Steve Merchant, so.
Oh, okay.
I thought maybe.
I don't know who Steve Merchant is.
Maybe it was the one that you painted, but he is Ricky Gervais's writing partner.
Ah, okay.
Co-wrote The Office and Extras.
Okay. And I thought he was the mayor of Terryville, Connecticut, where I live, because our mayor is Mayor Merchant. So. Yes, he is not.
No, but I think one of the weathermen in your state, I don't know whereabouts, but is Joe Moravsky from American Ninja Warrior.
You told me that.
Well, keep your eye out for him, because I am really surprised he's never won the $1 million prize yet.
Wow.
I'm really, really surprised. He is that good. It's just a matter of time. So
amazing. Just so everybody,
a local town millionaire.
So everybody knows. By the way, I'm just taking several 30-second shots of the Crab Nebula, so I can do some processing, some rudimentary processing to kind of get an idea of how well I can get it to look. Now, when it gets up higher in the sky, it's just going to be far better even than this. But I see the Orion Nebula right now. It's up, but it's even lower than this. So as much as I really want to go steer into it, it won't be as pretty as later on.
Daryl just said there's a neutron star in the heart of the Crab Nebula. It spins 30 times a second.
Yep, that's the Crab pulsar. And one of the things that's interesting about these pulsars, a pulsar is the leftover stellar core from a supernova, and the thing about pulsars is that they spin very rapidly, and the thing is that's not how fast the original star was spinning. The original star was spinning much slower. However, when you have an explosion of the magnitude of a supernova, what ends up happening is the material, when the explosion occurs, because of the nature of the star, the material around the star, the spherical envelope of material around the star, the plasma, the rest of the material, the other burning, fusing materials, they're not in evenly distributed layers and shells. It's not like an even onion skin all the way around. A star is like an onion, Okay, different layers sometimes can be doing different things. You have radiative layers, that is where there's just radiation. You have convective layers, like in a pot of boiling water, usually in the outer atmosphere of the star. And when a star goes supernova, you've got all this going on. And the convective layers in the outer part of the star sometimes put these giant blisters on the outside of the star, and sometimes change the distribution of the material in the star, so that when the fusion processes stop, and that's usually at iron. They can't go past iron 56, which is one of the iron isotopes. When it stops at iron, okay, there's nothing else to confuse, and so a star lives its whole existence. And live, we use as a figurative word. A star exists through its whole existence as a delicate balance between outward radiation pressure and its own gravity. So when those are balanced, then you have what's called hydrostatic equilibrium. The star is balanced. There's forces that are pushing out equal to forces trying to collapse it. All right, the force trying to collapse it, of course, is gravity. So when the radiative pressure outward suddenly stops, because fusion just halts, comes to a dead halt. When that happens, then the star begins to collapse. And the collapse could be fairly quick. Now, the collapse starts, inside all the way to the outside. However, one of the things that is important to understand is it doesn't happen evenly all the way around. It can be more pronounced on one side versus another. It can be something where the collapse is, I should say, I don't know how to say this now in a way that makes sense. The collapse is not homogeneous. It's not even all the way around. I guess I have to say that. And if it's not even all the way around, what that means is when it finally does collapse, the material hitting, say, one side of the star is pushing, one side of the core of the star is pushing that core. All right? And then when other material comes in, sometimes that material can, help impart more spin that the previous material did, and the stellar core begins to spin. This is all happening in a fraction of a second. So some of these stars can be massive, but the collapse takes place in just a fraction of a second. And the collapse isn't the entire outside of the star just coming down and slamming in. It's the core of the star. The outer core of the star is collapsing into the center of the star. That happens in an instant. And when that happens, you end up having a supernova occur, because what happens is the stuff hits the core. And it's an iron core. It can't go, it doesn't have any give. It doesn't go anywhere. And when that iron core is struck, then then what happens is that the entire balance of the star, the rest of the star, all of the material outside the star, all of the material that's in the core that was collapsing, all that stuff gets thrown right out of the star again. At a very high rate of speed, and that becomes the supernova remnant that we see. And it's really fascinating. Really fascinating. Ow! bright white light. A fascinating thing that happens in the star, and above a certain mass, these stars can become neutron stars, and when they become neutron stars, they actually can be very very small. You know, a teaspoonful of neutron star would weigh several billion tons. Okay, and I know that's almost impossible to believe, but it's true. And this is something that's, you know, in physics that you have to just be able to accept once you actually see the data. You know, it's just incredible. But that said, you know, if anybody has any questions about this, I'm happy to take them. You know?
We do. I was just checking, and let me get the name of it again. I just posted it in chat. ERRTradio.com. Our friend Ronald is streaming this as well from his site.
Okay.
So you can go there and check it out. I was just looking. Everything looks good. Yeah, because when we were talking about neutron stars, Ronald wanted to know, how big is a neutron star compared to our sun, or do we know how big it is when it was a star? So I guess they all depend on how it kind of, not decomposed, but fell in on itself.
Yeah, well, yeah.
Like there's no specific size.
Well, it depends. Yeah, yes, there can be a specific size, but it's like trying to figure out the exact size of a original progenitor. They're called progenitors, the things that came before. Progenitor stars, when you have a neutron star, is tricky. But if you can get the mass of the neutron star, it kind of gives you a rough idea of what it might have been. You know, what kind of star it may have been. Because what we see, and the way we actually figure this out, is by looking at what we see in the supernova remnant. Sometimes the supernova remnant has a spectrum that indicates that certain elements were manufactured, all right, in the star. And that spectrum is very important, because that spectrum tells us if the star had enough mass to be able to generate elements, these elements of these certain types that we're seeing. And so by looking at the spectrum, we can actually see what's actually been made in the star, and that gives us an idea of what type of star it was. It's just, you know, it's a whole science, obviously, you know.
Can you tell us about the, oh my god, sorry Daryl, about the Chandrasekhar Limit?
Yeah, the Chandrasekhar Limit is actually...
Close.
We're close.
I was close.
The Chandrasekhar Limit is actually a limit that's... what is it? Well, if a star is above 1.44 masses of our sun, and we use everything in the terms of masses of our sun because we understand the mass of our sun, okay? Anything above 1.44 solar masses will be a star that will probably be able to shrink down to form a potential black hole. Okay, and I think that the most important thing to take away from this is that when Chandrasekhar, who was the name of an astronomer, by the way, when he came up with this limit, okay, he had plenty of evidence to indicate, what it meant. Okay, so hang on, I'm just looking at something here, just so you know, I'm not being flaky. I'm just checking something out here. So give me 1 second. 1 second. So, above 1.44 solar masses, that's sort of like the magic number. Okay. Now, if you have a star that's below that mass, then a star that's say a star kind of like our sun, maybe a little more massive, as long as it wasn't beyond 1.44 solar masses, then it will probably end up forming a white dwarf when it dies. if it's below that 1.44. Above that 1.44, then other things can happen. But below it, you end up with a white dwarf. And white dwarfs are basically, they have carbon and oxygen on their surfaces. And a white dwarf is, it's not quite the same as a neutron star, but the white dwarf is subject to something called electron degeneracy pressure. And this degeneracy is something that's a state of the atoms on the surface of the white dwarf that have like a pressure that pushes back, and it helps keep the star stable at that smaller size. That's a white dwarf. Okay. Now, neutron stars are smaller even, and these smaller stars, which are only a few miles across, by the way, are are literally neutron-degenerate stars, or they have neutron degeneracy. And neutron degeneracy is where the star's surface is composed entirely of neutrons. All right, and if that's the case, I think that what this means for us is that when we look at a degenerate surface on a star, it means that certain processes that happen on a star require a certain mass in order to happen. And so when we see that, we can say, oh, the star is a certain size, therefore it did this. Okay. So the Chandrasekhar limit itself is that minimum, okay, that you need, the minimum mass for a stable white dwarf star. And that's something that, like I said, beyond that, then you get other things happening, okay? You can get a supernova. And in fact, one thing that's interesting is if you have a, say you have a white dwarf, okay, which is the end state of our sun eventually, it's going to be, and say that there was another star nearby, and that other star actually was bleeding or leaking material onto the surface of the white dwarf. Then what could happen is that star, the white dwarf, could end up literally becoming what's called a type 1A supernova. All right, it could explode. Now the thing is, when a white dwarf has this type of explosion because it's accreting or gaining material from a nearby star, that explosion is actually a bigger explosion than the explosion of a star that just goes supernova. All right, so a massive star going supernova can produce an awful lot of energy, like the Veil Supernova Remnant that we've seen. And right here, this one we're looking at right now, the Crab Nebula. And these supernova remnants are moving outward into the interstellar medium and dispersing these elements that were made during this explosion. And that's what we're seeing with this. We're seeing this happen here. And this is just, incredible because, this we know that the star here was more than 1.44 solar masses. We know that the star that was the progenitor for the Veil was more than 1.44 solar masses. It had to be, because if it wasn't, then we would have a white dwarf and possibly a planetary nebula. Because a planetary nebula is a star's, it's sort of a slow death of a star. Okay, a supernova is the most dramatic cataclysmic death of a star, but a planetary nebula forms when a star is dying in a far more slower way, far more what's the word? It's still an act that's got a lot of complexity to it. There's all kinds of shock waves that move out at supersonic speeds from a star when it's doing a planetary nebula stuff. But I'll tell you, it's the when we talk about this in a way that in a way that actually let me see here. Hold on a second. I'm just checking something out. All right, there it is. Okay, sorry, I had to. I'm trying to make something happen here, and it wasn't happening. Okay, why is it doing that to me? Just a minute. Okay. All right, we're there. I'm sorry. You know me. I'm doing 5 things in here at once, and so I was trying to get my telescope connected again to the Wi-Fi. It disconnected for some reason. So rather than lament about it, I just fixed it while talking to you about the Chandrasekhar limit. So I hope that answers the question about the Chandrasekhar limit. But if there's more, I'm happy to pursue it, and I'm and happy to fill in the holes if I left you any holes. So.
Yeah, I think that's all right.
Okay.
No, there's just a bit of discussion about, what size that specific neutron star would have been before it exploded and collapsed and everything. And Daryl just said if it had enough mass, it would have become a black hole instead of a neutron star.
That's correct.
So now Ted's asking, at what rate do black holes consume the space around them?
Well, that's a tough question because they don't necessarily consume any of it. A black hole is basically a star that has collapsed beyond white dwarf stage. In other words, overcome what we call the degeneracy pressures. Okay, so it overcame the the electron degeneracy pressure that would be needed to stabilize and hold a white dwarf stable. It overcame neutron degeneracy pressure that could hold a neutron star stable, and it went right on past it to a black hole. Now, sorry again about the cough.
Does that mean nothing is stable?
No, it just means that every stability has a tipping point. Every stability.
But what's further than a black hole?
Well,
why does it stop there? Or does it? Do we think it stops there? Like, do we think maybe there's another level we just haven't proved it yet? Or
I mean, beyond black holes?
Yeah, like what you said, when it reaches certain points, it can't degenerate anymore. It moves on to a new thing, and it can't degenerate anymore until it's a black hole, and that's it.
Well, once it's a black hole, that's the end state for that particular massive star. And we don't really even know what the black holes are. I mean, we do. I mean, we have mathematics that can describe the activities that go on at a black hole. The black hole has what's called an event horizon. It's that point on a black hole where you cannot, where light can no longer escape. If you just go past that event horizon, light cannot escape a black hole at that point. It's actually it's a fairly well understood thing, actually, for black holes. But let me tell you, there's not there isn't a book out there that can tell you all the secrets of the universe, and black holes certainly hold quite a few secrets that we don't understand. Like, again, are black holes just like a drain into another universe? We don't know. And there's one spot in our universe where some astronomers had looked at this one spot in our universe that looks like it's actually draining, the material is draining out of our universe. It's not a black hole, but it's just something that's an area in our universe where it seems like this stuff is draining out of our universe. And what does that mean? We don't even know. We don't even know. So it's crazy. It's actually pretty wild. So I know I'm going on and on here, but
no. Well, I was gonna say, light can't escape a black hole. Do we know, can gravity escape a black hole?
Well, that's the thing. Okay, we know that light can be bent by gravity. Okay, because and that's the opposite side of what you're saying. And that actually proves Einstein right. Light escapes a black hole. Light escapes a black hole only if it doesn't ever enter the black hole. Gravity, on the other hand, because of the gravity waves that we saw with the merging neutron stars, we figured out that gravity actually has the same type of fall off. That is to say, it gets weaker with distance, as light does. So gravity gets weaker, and it's not because of merging neutron stars. Okay, I can tell you more about that in a minute. Gravity gets weaker by the square of the distance away, and we can just calculate that by looking at the planets and working through the math, and we did years and years, a century, I think more than a century ago, and a couple centuries, and so that's one thing. But when the merging neutron stars were seen, we saw something else predicted that by Einstein, but Einstein himself said we couldn't see it, but we did, and that was gravity waves. Okay, we saw a propagation wave of gravity from this merger, and that, you see, we had never seen. Now, I was very excited by this because I felt that this meant that the next step beyond this would be perhaps that we might see perhaps a gravity particle, perhaps. Maybe a gravity particle is not far off, in this type of arrangement. Maybe we're talking about being able to see gravitons, so to speak. So I don't know. I just think that that's a pretty cool possibility. Ouch. Just hit my head on my telescope.
Please don't do that.
I did. It's cold. I can't even tell I hit it until I feel the pain. All right, let's see. All right, let me just go to this next object here. All right, okay. We're at the crab now. Let's do something now different. I'm going to go here. Let's see what this does. Here we go. Oh, I'm very cold. I'm sorry, guys. Okay, so now, oh, and of course the battery's dying. Okay, so I have to get a new battery, which I'm doing now. And I'm going to turn it off for a split second so you don't get to see that object that we were just at.
Ooh, was it something we were at earlier?
Nope.
Did you show me earlier before the stream started?
Nope.
Really?
Uh-huh. Yeah, see, you thought we did. No.
No, well, I saw a comment scroll by and...
Wasn't that. I'll show you.
Was it a little version of it?
No. Okay. Alright, so let's see me. Whoa, I may have to go in and get warm. Okay.
Just as you said, Burr, Ronald said, when you moving to Arizona.
Oh, I can't move
soon
enough.
Warm there.
Can't go soon enough, I'm telling you. God, the controller to touch the telescope, the Wi-Fi, the iPad face is so freaking frigid. Okay, let's do this. Let's go. We don't even need a very high ISO for this. Let's go down to, say 4,000, and we'll do 10 seconds. I'm doing 10 seconds because I want to see if we can see fine detail in this nebula, or if we can't. Shiver, shiver. Okay, let's see here.
It must be really cold because you haven't been out there for that awfully long. Ooh.
Yeah. Yep, this is the Orion Nebula, folks. This is M42. M42 is an amazing stellar nursery, and it's powered by the 4 stars in the center called the trapezium. And those 4 stars are...
It was the trapezium.
Huh?
It was the trapezium.
What's that?
You showed me the trapezium earlier. That's what scrolled by, the little trapezium.
No, the Orion Nebula wasn't even up when we were on earlier.
Well, maybe it was a picture. I thought I'm sure you said it was a triangulum.
Yeah, that's Triangulum. That's a Triangulum galaxy we saw. That's right. That was in the constellation of Triangulum. Trapezium is different.
Oh, okay.
There you go. Yeah, this is telling me that you know, we have to wait a little longer for this to come up, for it to be better. But I'm just gonna go do a 15-second exposure at. No, I'm not. I'm gonna do a 1600, and I'll do 20 seconds just to see what happens.
And I'll just let chat know, because, as always, I've said this so many times, and I just want to let you guys know that the curse is still with me. Because it's the Leonids tonight. It was pouring rain, and I thought trees were going to come down. It was that windy. So, again, any kind of event in the sky, it's going to be rain or snow or fog or something, and I won't see it. So, thank caster people like Mark and Bill that actually stream these things for us.
No, I think that you want to also kind of make sure that you just don't live in Sydney, Nova Scotia.
Yeah. If there's anything you can do to prevent that, do it.
I'll try. Which I think I'll fail miserably. Oh, okay, telescope is still nice and dry. Outside of the building is very cold, but dry. Okay. Let's see what I got here. Alright, I'm going to leave it here. Alright, here's what I'm going to do. I am going to actually go in and get a little bit warm, and I shall return. Now, I don't...
It's a two-parter tonight, folks.
I know, I don't have... I'm sorry about that. So what I'm going to do is I'm going to close the stream down for a little while, and then I will come back. All right? And when I come back, we will look at this nebula in far more detail, if we can. And when Orion gets higher in the sky, we are going to check out some elements of the Orion Nebula and these environs around it that might actually, be visible to us. Which, there's some areas around it that, right now they're lost in the murk right now. But when that gets higher in the sky, it's going to enter darker sky.
It's so gorgeous right now. I can't. It's.
This isn't good at all.
To say it's in the murk and it's not that great. It's going to be so much better. I mean,
yeah,
that's crazy.
I know, right?
This is gorgeous. It looks really clear. It looks absolutely stunning to me. So.
Well, that's good. I'm glad it does. But
I really like this one. I don't know if it's the shape or the colors or what, but this is very eye-appealing to me. I love this one.
It's full of colors.
It is. It's gorgeous.
But so,
give us a rough idea of when you might be back, an hour or two.
Yeah, it's probably going to be no less than an hour. So I'm going to go in, I'm going to get warmed up. I got a heater already running in my office. And I'm going to get warm because I'm shivering right now. And my heaters in my shoes and in my gloves are already being working well past their design limitations or design specification. So I'm going to do this. I'm going to close the stream, and I will have you, I'll be looking forward to seeing you come back in about, let's say, what time is this, 9:22? Let's say 10:30, okay? 10:30 is the minimum, all right? And I'll be back at 10:30 to do more.
That's Eastern Standard Time, everybody.
That is correct. Sorry. Thank you very much
and
for saying
hopefully everybody, I don't know, maybe Arizona's back on track. Hopefully everybody did the daylight savings time, fell back about 2 weeks ago, so...
Yeah, Arizona doesn't change their clocks.
No, I know. So in my mind, they've been an hour off for the last 6 months. So maybe they're... But yeah, so okay, so 10:30 Eastern.
Yeah, I think they're 2 hours off us now, and sometimes 3. So, but they'll be or 3 hours off you, and sometimes 4. So.
Yeah, but I mean, we have Andy in England who is 5 hours ahead of you, and Daryl in Colorado who's what, an hour behind you, and
yeah, he's on Mountain Time, I think. Actually.
Yeah.
So.
No, that would only. Is that? No, he's 2 hours behind you because he's 3 behind me.
Yeah, he's Mountain Time.
I gotta let everyone know it's Eastern Standard Time, 10:30 Eastern Standard Time.
Right.
So like 2 hours, basically. No, 1 hour.
1 hour.
What time? 10:30.
You're amazing.
Eastern.
Yeah.
In about an hour, in approximately an hour.
Yeah.
Set your clocks.
Yeah. If
people are asking if there's going to be a notice. I mean, if you hit the bell, there will be.
Yeah. But it'll be. It's probably going to be 10:30 minimally. Okay, and it's not going to be like a thing where I just disappear and never come back. I'm going to be back at 10:30. I'm actually leaving the dome open and everything. So I just have to go in, get warm. I got to let Orion rise higher. I got to let the Crab Nebula come up higher. And then we will be able to come back to these things and see them and just really have a good time with them, okay? So I will see you in a little while. And
22:30.
I will talk to you in just about an hour. All right, folks. So
see you later.
See you later.
So go over to Bill NY Skywatcher, everybody. Chill there for an hour, and
we'll poach you back. We'll poach you back when we're doing our thing.
Thanks for the support, as always.
Thank you, guys. I'll talk to you soon.